Can fusion energy contribute to a fossil-free energy system? What an interesting question, and important.
Exactly.
Most welcome to the seminar to all speakers and participants, both here at IVA, but also on the web. This seminar will be in English due to participants from all over the world. My name is Ulla Sandborg. I'm the Vice Chair of IVA's Division 2, Electrical Engineering. And IVA is the Royal Swedish Academy of Engineering and Sciences. We are about 1,300 Academy Fellows and 250 member companies. IVA was founded over 100 years ago, so we had a celebration in 2019 for 100 years. I think we are the oldest one in the world. Yes, that's nice. This seminar has been organized by Sonja Berlin. She is a recent elected member of IVA and our division, and also professor at KTH. She used to work with research at the Norwegian TSO, transmission system operator, Statnett, for many years. And she will talk about European climate goals, first of all, and then Thomas Jonsson, a researcher from plasma physics from KTH. We'll talk about principles of fusion technology. And after that, Tunde Philip will talk from the same plasma physics, but from Chalmers, in Gothenburg. She will talk about current research activities, so we will be fully learned about these things. After that, Robert Bergqvist, he's the Vice President of European Business Development at General Fusion, a company, of course, working with fusion. He will talk about his company and also about challenges they meet regarding this topic. And last but not least, Dr. Michel Laberge. He's the founder and chief scientist of General Fusion. And he will talk about the technology that General Fusion is using. And by the end of the seminar, we will have a debate. It's moderated by Sonja here. I'm looking forward to that. So by the end of the day, hopefully, we know more about and are much more enlightened about fusion energy. And we will end the seminar around 7 o'clock. And by that, I leave the words and the floor to Sonja, and you will talk about European climate goals.
Thank you, Ulla. So we know each other from before, so that's quite good. So now my presentation will come up. This should be a debate, and to be able to get a debate, we should sometimes be a little bit provocative to get this good debate discussion, because if everyone agrees with each other, there will be no debate. So the hypothesis of today: can the fusion be a solution for a carbon-free energy system? And the reason I say this is the following: is that the European Commission have set extremely ambitious climatic goals. We should be the first carbon neutral continent by 2050, and this means that we need clean, affordable, secure energy. We should have a clean and circular economy. We should also improve people's health and quality of life. We should care for nature. We should boost the economy, and most of all, not leave no one behind. We need to do the financial transition. We want to go for a toxic-free environment. We want to preserve and restore our ecosystems, and we want to have a fair, healthy, and environment-friendly food system, and then we want to have sustainable and smart mobility, amongst others. And what does this mean? Because this is words, and everyone, all the activism, they're out there protesting and painting a very black picture. I mean, of course, it's not good what is happening, but there are actually solutions. Already in In 2018, there have been done studies that is this actually possible to stop and maybe even reverse the climatic change? And yes, it is. We have the technologies available, maybe not at the technology level or in industrial readiness level as we would like to have, but actually the solutions are out there. So what is it that we need to do? What is the most challenging actually that we have? Well, the most challenging is to decarbonize the heavy industry in heavy transport and the heavy industry. But if we look at all these things that need to be done, which you can read in detail in these reports, this will lead actually to a massive electrification. And this will lead to an increase in power demand by a factor 4 to 6. We were talking a little bit about it as that many politicians and out there are talking about, you know, flexibility, and that will be save us all. And I make a comparison to a car. So if you have a car that's made for 4 person and you want to have a little bit flexibility, you put a roof box on and you have maybe a trunk that you can store the luggage, and that will maybe give you room for 5 persons in the car. But here we need to fit 16 persons in the same car. And so then everyone understands that flexibility will not be the solution. We need a different car design. And I think Ulla and me have been working with that before. And this is a huge challenge. And if the demand for electricity is increasing, what does this mean? That means that we need to increase the supply as well. And also we need to increase the production, which is also, the transmission, which is also challenging. And then you will understand we're talking about, you know, 4 cars instead of 1. Then you also maybe start to understand that maybe wind power alone and solar roofs, solar panels on our roofs will maybe not be the solution. So we need different solutions, and we need carbon-free solutions. And I really hope that then by fusion power can be a solution to this. So hereby I invite the first speaker to tell what is actually fusion technology and how can it help us to reach these climatic goals. So.
Okay, can you hear me? Yeah. So my name is. Okay. No, you cannot hear me. Turn it on. No. Is it okay? So, my name is Thomas Jonsson. I'm an associate professor at the Department for Fusion Plasma Physics at KTH. And I will talk a little bit about the basics of fusion power and fusion technology. So I will first talk a little bit about fusion reactions and the fuel we need for fusion, then some principles of reactor design, and at the end I will talk about the ITER experiment, which is a large device that is being built in southern France right now. So the sun is a fusion reactor that powers the solar system, and that has been an inspiration for scientists for decades. Could we bring this process to Earth and utilize it to produce clean energy? However, the sun is actually a very slow burning reactor. It has been burning for billions of years, and it will continue for billions more. So all the fuel that is in there is not being depleted very fast. And if we want to build something on Earth, we have to do a lot better. In fact, if you take a cubic meter of the very center of the sun, it produces about 280 kilowatts. Watts, not kilowatts. Watts, which is, considering it's been burning for over 4 billion years, it's an enormous number. But if we want to do something on Earth, we have to do a lot better than this. And the solution to do better than the sun is to change, first of all, the fuel. So we need to go to better isotopes of hydrogen. In the sun, they use pure protons as the main component of source of fusion. In the fusion reactor on Earth, we have to use the hydrogen isotopes, deuterium and tritium, and we fuse these together to form helium and a neutron. And in this process, we release 17.5 mega electron volt of energy. So that means that if you take if you could use 0.7 grams of this fuel, you would produce the amount of energy that a person needs for a full year. So deuterium is something that we can extract directly from seawater. This is a fairly simple process. However, tritium is radioactive. It has a half-life of about 12 years. So there is no natural tritium on Earth, and we have to produce it. And we can produce it from lithium. And in fact, if we can do this in a reactor, because from the deuterium-tritium reaction that we have, there's a neutron being created. And this neutron, we can let that hit a target of lithium, which then it produces a reaction that creates tritium and helium. So the rest product from this chain is helium. So the resources we need for fusion are water and lithium, and we have vast resources of both. But the catch here is that we need very high temperatures. We need 200 million degrees, which is 10 times hotter than the center of the sun. But there are also a few other things that, of course, that we need if we want to commercialize anything. We need to build some form of system where we have this 200 million degrees hot plasma. And of course, that's going to leak out energy. So we have to make sure that the fusion energy is maintaining this high temperature. And to do that, when we do that, we can get very simple condition for when fusion starts being viable. And that's when this triple product, as we call it, the product of the density, temperature, can I point with this guy? Maybe, yeah. The density, temperature, and confinement time, when this product of these three is sufficiently large, then fusion is possible. So this condition leads then to naturally to two different distinctive roads to make fusion reality. The first one is a steady state road. So you create something that operates in steady state. It's a continuous operation. This is usually achieved by magnetic fields. And it allows you to go to very long confinement time, which is basically the time scale that plasma leaks its energy. And you can, on the other hand, operate at fairly low densities, which is helpful at this high temperature. The other route to fusion is what I would call implosion explosion. So in here you use either lasers or magnetic fields to compress your fuel to an extremely small target. And in the compression, the temperature rises to thermonuclear temperatures, and the nuclear reaction starts then to increase even more the pressure, which means that the target is going to expand in an explosive manner. So this gives us very short confinement time, but extremely high densities. So these are the two main routes, and we're going to see first in my and Tinder's talk, we're going to talk about magnetic fusion, and then in the later talk by Robert and Michel, we're going to hear about magnetic compression. So I work personally mainly with magnetic fusion, and here we have the obvious problem. We have 200 million degrees, and we have to put it in some form of container that doesn't melt. Now, the solution to not making it melt is to use magnetic fields, because at 200 million degrees we have a fully ionized plasma, and so all the plasma particles will then spiral around the magnetic field lines according to the Lorentz equation of motion. And the magnetic fields that we have to have certain geometries, and the most successful geometry we have so far is a toroidal system. So we set up a set of complicated magnetic field coils to generate a very specific, robust magnetic field that is robust to perturbations and will provide a stable confinement system. So this particular system that we show here is called the tokamak, and it has a number of coils, something called the toroidal field coils, that is producing the main magnetic field. Then there are some poloidal field coils, and in the center we also have a solenoid that uses transformer action to drive a current inside the plasma, all part of the confinement of a toroidal device. So once we have a plasma that is hot enough to start producing fusion reactions, we will get neutrons, and the neutrons carry 80% of the fusion power. And neutrons are not electrically charged. They will not experience any forces from the magnetic field and will go straight out into the surrounding walls. So this is part of the walls in the design for a future reactor. And the first wall that you see here, the gray part, is actually very thin. So most neutrons go straight through these gray parts, and instead are deposited in the blue area called the blanket. So in the blanket, the 80% of the fusion power that is carried by the neutrons will be deposited inside this blanket, and therefore heat the blanket. We then use cooling water to transport the heat out of the system into a generator where we can produce electricity. In addition, the blanket is primarily built of lithium. So when we have neutrons bombarding our lithium, we will produce the tritons, the tritium, that we need for further operation. Okay, so fusion technology has come far enough to start building reactor scale devices. And at the moment we are building a very big device in southern France, which is collaboration between US, Europe, Russia, India, China, South Korea, and Japan. It's more than half of the world's population. And this is an illustration of ITER here. It's very big. It's about 60 meters high. And as kind of hinted by all the structures around here, it's also a very complex device. But it's under construction now. The first plasma is expected in 2025. The first deuterium tritium plasma is expected in 2035. So that's when we will start producing high amounts of power in ITER. And we are expecting ITER should produce 500 megawatts, which is really reactor scale powers. At the same time, as we're producing this 500 megawatts, we need to inject about 50 megawatts to keep the temperature of the plasma, which means that we have a gain factor that we call capital Q equal 10. So this capital Q is really the ratio between the fusion power and the input power that we're investing in the system. So this is not a power plant. It will not produce electricity to the grid. It's a research facility to show that fusion can operate at fusion relevant power and produce fusion relevant gain. In addition, ITER has a very important role in developing the physics understanding of these large devices. We have never built anything this big before, so we need to understand how the physics changes when we build bigger in order to optimize future reactors. Also, we need to develop technology, fusion technology. So many of the components that are in this system are really extreme. They are first of a kind or breaking records in one or the other ways. So I want to end my presentation with a few pictures from ITER. So this is the ITER site. It's about 1 kilometer across. In the center is this the ITER tokamak building. And if we go inside, now maybe this is little bit dark here, but over here is the reactor, the tokamak area. So this is where they're now building the tokamak. And on the right we have the assembly hall, where all the components that should go into the tokamak are being prepared for before being assembled. So here we have, for example, a few pieces of vacuum vessels that we see from the top, so they're not very illustrative. But we also see a field coil here. It doesn't look very big, but it is actually very, very big. It's this big. So it's 17 meters across, and it weighs 350 tons. And actually, they just recently installed this. Now I have a video here, but it's not starting. So I will just tell you. In September, they installed this coil into the tokamak here. So they are really building the tokamak right now. Okay, that's all from me, and I leave the word to Tynde to talk more about ongoing research activities.
Thank you very much. And you know, compared to the enormous wind power they are building, we need thousands of these. But it's much less land use, so that might be interesting. Okay, then the floor is yours, Tynde.
Can you hear me? Yes. Great. So I'm so happy to be here with you in real life, and thank you, Sonja, for taking this initiative. It is wonderful to be here and talk about these exciting developments. So I will talk about current research activities and a little bit of future outlook. And my name is Tynde Fulop. I'm from the Department of Physics, as I was introduced, from Chalmers, and I've been working in theoretical plasma physics. So I'm not working with these beauties directly. I will come back to this in a minute, but I will start my presentation by talking about tokamaks, which was introduced by Thomas, because tokamaks is dominating by far the magnetic fusion activities. It is axisymmetric, so it's fairly simple design. Nothing is simple in reality, because it has to be a bit twisted, so we have to have also a large current. So the toroidal field is produced by these red coils, but then we also drive a current, as Thomas mentioned, by transformer action. And the reason it's dominating, because it has achieved values of the triple product, this fusion triple product, density, temperature, and confinement time, which exceed those of any other concepts in the field. So there is a large number of tokamak experimental facilities operating or being constructed all over the world. And I will just have time to show you the largest ones. The currently largest operating tokamak device is the Joint European Torus, which is in the Culham site outside Oxford. It started in the beginning of the 80s, so it's been around for a while. And it has produced fusion power, a couple of, like 16 megawatts, 97. It's not nothing. I mean, it is a proof of principle, but they have changed the walls and refurbished and made changes. And now, as we speak, they are putting in deuterium tritium again. And I'm hoping that there will be records broken during these, maybe during this seminar. So the major radius is 3 meters, and you see this man standing there, so you get a size, magnetic field 3 Tesla, approximately volume about 100 cubic meters. JET was designed and built in the beginning of the 80s, so it has copper coils. Back then, it wasn't possible to have superconducting coils, so we can only operate a few seconds because the coils become hot. So nowadays, every machine we build is with superconducting coils. So there is a sister device, maybe I should call, GT60 Super Advanced, which was just completed in Japan. This is actually a collaboration between the European Union and Japan. You see the Japanese flag clearly, but actually there is an EU flag there. And it has been, it's approximately the same size. You see the volume is slightly larger, major radius about the same, but it has superconducting coils. So when it starts operation, it will become much longer shots. And so this is very interesting. So tokamaks, as I mentioned, it has been impressive fusion performance. So it has enormous technical and scientific base. So we have built lots of tokamaks across many years, many decades, and the first 3 decades, the evolution of the triple product was exponential, so it actually exceeded Moore's law for 30 years. So then we had enough confidence to put everything together and let's build a larger device, which would get over so-called break-even when this gain factor is larger than 1. But unfortunately, that is so large, so there has been stagnation due to the size and the cost. So, you know, I'm not known for my patience, so I was rather fed up with this stagnation. But now, as Thomas mentioned, we see the light at the end of the tunnel, so it will actually be started in a few years. But in the meantime, there has been an amazing progress in the development of high-temperature superconducting magnets. So if you look at this horizontal axis is the years from 2009 to 2021 and the magnetic field, and you see that you can build large magnets like 40 Tesla. And there is actually, for the gain, there is a trade-off between size and magnetic field, which unfortunately I can't prove it to you, but you have to believe me. So if you plot the gain, the fusion gain, then if you have a limit of maybe 5-6 Tesla, then you have to build a large machine to be able to have a gain which is larger than say 10, which we want to be. But if you are not limited, if you can have higher magnetic fields, then you can go down in size. And this is what they aim to do in a collaboration between MIT and actually a private company, Commonwealth Fusion Systems in the US. So they will actually, this is small enough for a single lab to build, so you don't need the half of the world population, so they can actually build it. And they will have a volume of 15 cubic meters, which is a 60th of ITER's volume, and the magnetic field of 12 Tesla, and major radius is 2 meters, which is actually smaller than the jet machine. And the targeted completion would be 2025, which has, you know, Americans, they want to come before ITER, probably. This is my, but the estimates, these 50, 140 megawatts and the gain factor larger than 2, that is based on conservative estimates, and this is in published literature. I have been myself co-author on a couple of these publications, so this is physics which is well established, so it's believable. Now everyone was holding their breath. Could they build the target, the magnet large enough so that they can actually produce these? Because of course in a lab you can produce 40 Tesla, but can you build a large enough magnet? And this is what happened just a month ago. So they have successfully tested, so this is just the size, they have successfully tested a prototype high field coil for high temperature superconductor for 20 Tesla. And it is amazing. I know 20 doesn't sound much, but that is huge. So the magnetic pressure for such a magnet is higher than what you have in the Mariana Trench, which is the deepest hole in the ocean, which is as deep as, you know, Mount Everest is high. So you can't really make higher because then it will break. So this is basically what they achieved. So now we are all hoping for that they can actually successfully build. They have the site, and we'll see. This is not simple, of course. If we come back to Europe, in the United Kingdom, there is an ambitious program for designing and building a prototype fusion test reactor until 2040. They are good at the spherical tokamak concept, so they basically, it's still toroidal, but they squeeze it. It's like a cored apple, so you take out the core. And the UK is world leading on this. They have built the first spherical tokamak, and they have the best one currently operating. And if you go up to a reactor scale, then it will be larger than the one they have currently, but it's still the size comparable with jet. Fusion power output would be in the gigawatt scale, so it's larger than this small machine Spark, which I only showed. Now this is, of course, you would probably wonder, you still have the same amount of power you have to get out, and it's a smaller size, so how you will do it? And they actually have a solution. They have a very clever exhaust system which they just built in mass upgrade, and they will test it. So we'll see. They have a plan, and I hope it works out for them. So this is ongoing in JET. There is a totally different concept which doesn't have a plasma current. This is what I showed you on the first slide. This is not a tokamak, it's a stellarator. So you have to have this twist in the magnetic field. In a stellarator, they impose it from the outside, so they don't really have the need to run a plasma current. So this is a 3D device, so the performance lags behind the stellarator, behind the tokamak, but we can't put all our eggs in one basket, so it makes sense to test different designs. And the world's largest stellarator is in Germany, and started 2015, and it had very good results. So they have shut down and put some more diagnostics, and now they will restart it in December 2021. So this has also superconducting magnets and 3 Tesla and so on. So I think I probably run out of time, so I will just say that there are vigorous activities all over the world. A lot of things I can't really get into, but the most important is that we have deuterium-tritium experiments ongoing at JET, which will give hopefully new optimism, and we have improved numerical tools, superconductors, machine learning tools for design, and also optimization, feedback control. We have also technological developments in material science, like superconducting magnets. So it's like a totally new world. And these experiments which I talked about, they have the aim for break-even. This figure, just I know we can't read this figure now, but this is this triple product evolution, where you have all the machines, even this Wendelstein machine is put in. So how you see how it sort of gets close to break even, and when the gain is larger than 1. If I have a couple of extra minutes, I can show you that also these are not my slide. I come from academia, so I'm not in the private business, but this slide shows how many private fusion companies have been started. This is from a recent report from UK Atomic Energy Authority. So you see 10 years ago we had maybe 8, and now we have 23, and they start companies all the time. And we'll have now one, so these are just the names, and General Fusion, the company who will talk next, is one of the oldest actually, and the one I mentioned, Commonwealth Fusion Systems, was established only 2018. So a lot of things are happening right now, which is very exciting. So I think I'll probably stop here, and we don't stop for questions now, or it's...
No, not yet. So we go. Thank you very much, Tunde. I think it was very interesting to hear about the enormous sizes of magnetic fields and the new materials, and actually what new development can do. So now to the next speaker. Please go ahead.
Är det jag härnäst?
Okay, then go ahead, Robert.
Okay. Can you hear me well?
Yes, we can hear you. Yes.
All right. And you can see my presentation as well, I trust?
Not yet. Now we can see your presentation. Good. So we both hear you and see the presentation. That's fantastic.
It is. And it's also fantastic to be here today. I'm very grateful for this opportunity. And I have our founder, Michelle, with us here today as well. So we're going to talk a little bit about one of these private companies that Tinde was mentioning. First, I will go for a 10-minute presentation on the commercialization strategy that we have, that we're working on until 2030. And then Michelle will go more into the technical depth of the technology and like why we have chosen this specific technology to commercialize. This is a picture of General Fusion. So we're one of the world's most advanced companies when it comes to fusion. We have about 15 years in the field. We're headquartered in Vancouver in Canada. We have about 130, 150 employees. And we're really a quite well-funded private company that has been pursuing fusion technology for a few years right now. And of course, it's all about meeting the challenges that we're seeing on increase of electricity demand and also a decrease of emissions. And what's really unique about fusion from a production standpoint is that it's a technology that is suitable for plannable long-term production of energy. It's scalable, etc. But it's also socially accepted. And that's something that is very unique and a great complement to renewable sources like wind, solar, hydropower, etc. So this is the foundation and why we see so much promise with this technology going forward. We have selected a specific technology that is called magnetized target fusion. And Michelle will talk about this in greater detail, but just as a top level from a business standpoint, which is something that I'm working with, the technology can be used for a lot of plannable, scalable power plant operation. The technology will lead itself to some kind of a small modular size of between 100 to 230 megawatt electric. We get effectively cost-free fuel. We have also a technology that is built from the beginning to work as a power plant, generating both heat and electricity. In this very schematical pictures, you can see how on the left-hand side, the entire machine is quite big when it comes to a comparison to a little person. So you see a small person there on the left in a red coat, and above that person there is a machine with a liquid metal core that is rotating, spinning. It's being compressed. We're using then a plasma injection system to inject plasma. The reaction happens, and then we convert that energy into or through a steam generator, and then run the steam through a steam turbine, and then electricity can be generated. So it's a fairly straightforward process for actually getting the energy out of the power plant. So not just a test of how fusion works, but it's really a machine that is meant to be used as a power plant in a commercialized environment. And the three things that we've been working on quite hard over the last 15 years, and that's also what's making the promise here for fusion or commercialized fusion by 2030, is that we can achieve the fusion conditions. We have a system that works for energy conversion to get the actual steam out and generate electricity. And we also have technology that is proven as durable power plant operation. When we're looking a little bit at the timeline, and this is really the message that I want you to get out of this presentation. Fusion is now. This is not 30 years into the future anymore. We're really seeing to commercialize fusion in the next decade. And at the top, you can see a timeline. So today, to 2005 and 2030. So right now, we're in the process of launching a demonstration plant, and I'll get back to that in a second here. We're going through engineering, design, construction, etc. And that's really supposed to be online and start to be in a commercial operation by 2025. Meanwhile, in parallel also, we are developing our commercial pilot plant. So this is something that then is going to be kind of a first mover power plant being operated by an operation company in 2030 and beyond. So our first commercial power plant where electricity or heat is generated. So why is then fusion happening right now? The standing joke in the industry is that fusion is always 30 years out into the future, right? And there are a few things that are absolutely crucial for us to have this working. So it's on the one hand side, it's the plasma physics knowledge, all the science that is being developed by ITER, STEP, etc. But in addition to that, the enabler is really around that advanced manufacturing techniques, and then also computational data power and big data analytics, be able to control the plasma and all these control systems in the machine. That's really the difference now just compared to 10 years ago. Over the 15 years that the company has existed, we have proven out three things. The technology development has been focused on three main areas. So the plasma injector, compression system, and then also achieving some kind of stability for the fusion process. So those three things have individually been tested out. Systems have been developed over the years to prove out that they are working. And what we just this year have come to an agreement with is to build this fusion demonstration plant, what we call FDP, in the United Kingdom at the Column Center for Fusion Power. And that's a power plant that, or not a power plant, it's a demonstration plant that will be built starting in the next year. And it has two goals. One is to demonstrate at power plant scale that it's practically achievable to do this. But then also over the next few years after it's been operational, we're going to refine the economics, how the power plant technology can be working in an actual environment. And this is a power plant or at scale power plant that we're doing at 70% scale of the real power plant, but it's never going to generate any electricity. The energy is just going to go into a heat sink. So it's a completely off-grid plant. And this is a unique project also in the way that it's being hosted in the UK. We're a Canadian company, but it's funded by three different governments. So Canada, the United States, and the United Kingdom. And we see that a lot of great things are going to come out of this demonstration plant. And that's then going to allow us to further work with the potential customers that we're now in dialogue with in Sweden, in the rest of Europe, and in North America and in Asia as well. So that's a process that we're going to walk on during the next 10 years to understand what kind of a role will fusion energy have in a kind of social environment. Will this be used for electricity generation, heat generation, generation of hydrogen, etc., etc. With that, I'll finish my screen share here, and I'll leave off to Michelle.
Thank you so very much for your excellent presentation. So then we go to the next presenter, Michelle.
Good morning. Thank you for inviting me at your conference. Are you seeing my slide properly?
Yes. Yes, we do.
Yeah, okay, good. All right, so generally fusion is done with tokamak with a density of 10 to the 13 or 10 to the 14 per centimeter cube. And there's another bunch of people that are trying to do laser fusion at density of 10 to the 25 per centimeter cube. Like there's like 12 order of magnitude here between a tokamak and a laser fusion. Now the tokamak needs a big laser, a big plasma, which have gigajoule of energy into the plasma. So this costs gigadollars. And the laser guy, they don't need so much energy. They only have kilojoule in their plasma, but they want to put this kilojoule in nanoseconds, so it's terawatt of laser power, and that costs terabuck. So both extremities are very expensive. So people, and a good engineer will look at that and say, why don't we go in the middle here at 10 to the 19 or something, where the power is only gigawatt and the energy is only megajoule, so it could possibly be made a lot cheaper. So this is the realm of magnetized target fusion. And what we want to do is we want to use a magnetic target, confinement with magnetic field, and squash it to increase its density. In the laser, there's no magnetic field. The heat escapes very quickly. But with the magnetic field, the heat escapes slower, so we can compress it slower. And that's what we want to do at General Fusion. So how do we do the plasma? So we use electricity injection to make our plasma. So this is a Marshall gun. This is symmetric. There's an axis of symmetry in the center. There's a bunch of coil here that makes what we call the stuffing flux. You see it here. And then you fire a capacitor between the inside and outside electrode, makes toroidal field here that push the plasma out the gun. And the plasma goes in the flux conserver here, and it reconnects. All those magnetic field reconnect, and it makes a closed surface magnetic field here that hold the plasma together. When we started that, we wanted to do a spheromac. In a spheromac, there's no shaft in the center. There's no toroidal field. It's all produced by magnetic field in the current in the plasma. Unfortunately, after playing with that for a few years, turns out spheromacs are not very good. They lose heat too fast, and they were losing heat faster than we were hoping to compress, so that was useless. So we need to compress faster than the heat escape. Then we put a shaft in the center. We run some current in the shaft that goes down and out here and makes a toroidal field. And if you put enough toroidal field, it becomes a spherical tokamak. And now, lo and behold, the confinement was much better. So those tokamak guys, maybe they have something, you know, it looks like a tokamak lasts longer than any other magnetic configuration. So we adapted that. So nowadays we form those spherical tokamak in the center. Then we squash it. So we have a rotating liquid metal that makes a cylinder cavity. There's a bunch of piston on the outside. And then we fire the piston and it pushes the liquid inwards. So there's a shaft in the center. This is the magnetic field here. And when you start compressing, we fire the piston on top a little bit ahead of the piston in the middle. So the cylinders start to take this shape here, this sort of bulging shape. And it goes in and it goes in. So you can see the liquid metal take this shape here. So the plasma gets smaller and smaller and smaller. And of course, temperature increase and increase. And at peak compression here, you have a spherical tokamak, which is, you know, about 40 centimeter in diameter and have like 60 Tesla in it. I will repeat that, 60 Tesla. Now, at 20 Tesla, you're at the bottom of the Mariana Trench. At 60 Tesla, you would break anything possible. But this pressure is supported by the inertia of the fluid, not by any material. So we don't actually break anything. The liquid will just bounce off due to this huge pressure and actually recompress the piston. So here's a little table of the sort of number we want. So we want about 2 times 10 to 20 per meter cube of initial density. That's about the same density as a normal tokamak. Sort of a keV temperature. And this is sort of normal tokamak number, but then we compress it 6.5 to 1 in linear dimension, and that's the cube of that in volume. So then it goes to 10 to 22, that's very dense. The temperature increased because of adiabatic compression, 38 keV. And then we make 488 megajoule of energy. And we only need about 4 meters square per second of heat loss because the plasma does not last very long. So because it doesn't last very long, you don't need good confinement. Now, those Tesla here are a bit scary, very high Tesla, very huge current, but this is due to the compression. When you compress the magnetic field, the magnetic field increase. You don't have to put those magnetic field, they're just generated by the compression itself. And this sort of magnetic field have been demonstrated in explosion tests where they compress magnetic field with explosive to produce very high magnetic field. Now, they won't exist for very long, but long enough to make our fusion happening. So this is the radius of the liquid metal as a function of time. It accelerates inwards for most of the time. So this is RT stable, Rayleigh-Taylor instability. The laser guy are very, very keen on this Rayleigh-Taylor instability because it wrecks their symmetry. But here it's stable all the way to in, but here when it rebound, it's unstable. However, we give a spin to the liquid because the machine spin, and the spin stabilizes the instability. Here's the temperature that shoots up 30 kV. In dash is the power that shoots up to 400 gigawatt. Now you look at that, 400 gigawatt, that looks like a low number, but it's only for a millisecond or so. So we have huge amount of power, but not for very long. So it's a bit like an explosion. So the plasma will not live for very long in the middle of that, in those conditions. Now the power plant will look like that. We will use liquid lead lithium to rebride, to make the rebreeding that has been explained before. So this is going to be circulated in a loop here. The tritium will be extracted, go in a boiler, make some steam, and we push the piston with steam. So this is going to be a steam engine essentially. So this is important because the recirculating energy here is from the steam. So it's pretty cheap and efficient. It doesn't go electric and laser, whatnot. And hopefully there's a bit of steam left to run the turbine and make some electricity for the power. Now, if you look at the number from the simulation, because we haven't done yet, it gives about 500 megajoule yield, another 100 megajoule because of the tritium breeding, which let go a bit of energy. We recover a lot of the energy directly by bouncing the piston. The piston goes in and out. So we recover 410 megajoule. We fire in 500. And then you can look at those numbers here. You need a bit of electricity to run the plasma injector, the pump, and the lights. And so it's about 115 megajoule left per shot. Now we want to run at 1 hertz, 1 time per second. So that 115 megajoule will make 115 megawatt. And for some odd reason, we think that the 200 megawatt power plant would be a better idea. So we put 2 core running 1 steam generator and 1 turbine. You save some money by ganging in like this. And if 1 core go down, you can keep running at half the power. But basically, 1 of those core will run about 100 megawatt. Advantage, we have lead lithium all around, full coverage. So no neutron hit the structure. And this is a big deal. A lot of the machinery will get destroyed by neutron in fusion. Those neutron, 14 MeV, very destructive. So a lot of tokamak have big problem that the inner structure gets wrecked by the neutrons. Here we only have liquid metal, so no structures damaged. We have a breeding ratio of 1.4 with natural lithium because we multiply the neutron in the lead. The tokamak guy would kill for this sort of breeding ratio. Usually they have a hard time reaching 1, which is what you need to keep on going. The heating is by compressed steam, so that's cheap. We can recirculate a lot of power for cheap, so we can run at lower efficiency than normal fusion because our recirculated power is cheap. The plasma is compressed in 1 energy confinement time. So the plasma exists for less than 1 energy confinement time. So there's no fueling required, and there's no impurity accumulation or helium accumulation because we only fire the plasma, compress it, and it flames out, and we make a new one. There's no current drive, which is a big deal. No neutral beam, no radio frequency. And the confinement requires about 4 less than what is achieved in tokamak today. So that's important because confinement is a big deal. And this machine requires less confinement than normal. There's no laser, no particle beam. There's no destroyed target each time. So this is good stuff. Like the engineering of this machine is very good compared to the other machine. However, we remain to be seen if at those very, very high compression ratio, the plasma still behaves. Like we extrapolate the scaling law from what we have right now, but we extrapolate them quite far because, you know, this is going to be a 60 Tesla plasma. Now, what have we achieved so far? We've made a 2-meter diameter plasma. This is the magnetic field as a function of time, last 25 milliseconds. It's important to notice we put only energy in the first microsecond, well, no, first 100 microseconds. And after that, this is decaying without being any energy added to it. Like the energy is dumped initially by the capacitor bank for 100 microseconds, and then that lasts 23 mics. It's an energy confinement time about 3.5 milliseconds, temperature of 200 eV, so that's not too bad. That's about what we would expect. Then we compress those things in a small plasma. This is the small can here. This is the equipment's built in container. We bring that in the field. We put high explosive around this metal here, and we shoot the high explosive, and it compressed the can with the plasma in it. Initially, when we started doing that, we had all sorts of crazy instability. So this is the magnetic field as a function of toroidal position at different time. So you start nice and symmetric, but then the plasma go all wonky. Eventually, we managed basically by adjusting the current in the shaft to track the correct Q profile during the compression, and we achieved that now, which stayed completely stable all the way in, which was a big deal. That's pretty rough. We shot a bunch of those explosions, and we changed the design here from there to there, so that's a bit slower. But what's important to notice is those crazy oscillations for a long time. But as of lately, you get a nice smooth compression. This is the magnetic field as a function of time. We all renormalized to 1 here because they were different. But you can see this one here grew nice and exponentially. The magnetic field does good. When we fire those things, there's reconnection, makes some neutrons. As a function of those time, the neutron decay exponentially. So this is an exponential in time here. So this is the neutron if you don't compress. And this is the neutron if you compress. So as the compression occurs, the neutron rate increases. Now, it doesn't increase as much as we wanted. We would like to go all the way to slap down is when the wall hit the shaft in the center. It stopped here. And there's still some problem here. We believe that when the explosives blow up, it shoots some garbage in the plasma and it kills it. Like the shock wave, any little piece of dust or something on the wall get thrown in the plasma. So we still have some work here, but it's looking pretty good. We see an increase in neutron yield. And if that's temperature, it goes from 200 to 800 eV. We're not sure because that could be a tail also. It's not necessarily Maxwellian. Piston, if you fire the piston, they will arrive at the end of the travel at different time. So we have a digital servo control system. And when we turn that on, the piston arrive out all the same time. That's important because those pistons will compress the fluid and you need to stay symmetric. So if it would fire like that, it would not be symmetric. And like this is nice and symmetric. And then we have liquid water that spin around in there. There's a bunch of piston around it. This is when we start. This is when we finish. So we compress that. We can see there's still a few little bumps and lumps here. It's not perfectly symmetric. So we are still working on improving the symmetry of those implosions. They're not bad, but we would like better. And then we're going to build this big machine in Column in 2025. Robert thought about that. So this is the sort of parameter that we will have in this machine here. This is the shaft current. This is the plasma current, the density, temperature to start. So this is kind of a normal sort of spherical tokamak. We're going to compress that in 4 milliseconds. And then the number become quite insane. You know, very big magnetic field, very big density, huge current, like a plasma current of 12 megaamp. By the way, this is automatic, eh? It's going to go from 1 megaamp to 12 megaamp just because of compression. We don't inject this plasma current. We don't have transformer or anything. The N tau, the triple product will be about this number here, which is about 10% of Lawson. So this machine will not quite make it to Lawson. It's about 10% of it. We have some plan to try to soup it up, basically increasing the density at the beginning, but that's just planned at this time. Right now, the machine is designed for about 10% of Lawson. Thank you very much. That's the end of my talk.
Well, thank you, all of you, actually. So I actually enjoyed the presentations because I see it's two different principles competing with each other, and that means that the environment will win, right? So now the floor is open for questions, if there are any. I don't know if there are any online. Maybe some here in the audience. We need to use the microphone so the question gets heard by the audience online. Yeah, there's a question here. So it's exciting with questions, as I had prepared some myself for backup. We'll see what we have here.
Okay,
go ahead.
I'm Johan Persson, and I have a question going back to the Q factor, because I don't get the math add up for ITER. Because you said that you have a Q factor of plasma from 50 to 500, so Q of 5. Oh, sorry, Q10. But that factor is not quite relevant from the total system point of view. Because if you read the literature, you see that the estimate of the input power for ITER is between 400 to 600 peak. So steady state is slightly above 400. So if we get 500 out, that's still just the plasma. We still need to convert that to something useful. So assuming we boil water and do the turbine thing, that's roughly 50% efficiency ratio. So then we are in a factor where we put in roughly 400 and we get out roughly 250. So that's nowhere near a Q of 10. So that's actually below break even. So can you comment a little bit on that, how this is actually supposed to be working full-fledged?
So the Q factor is a bit of it's a number that has been some debate around. Of course, if you want to build a power plant, you don't care about Q factor. You care about the net power that the power plant is producing. And now, since this is an experimental facility, we don't have the generators, and we don't have the systems to even measure, or we're not really interested in that factor. The ITER is designed for what we call Q equal 10, which is the ratio between the heating power, the fusion power, so the thermal fusion power, and the heating power that we're investing in maintaining this hot plasma. I'm not sure exactly where you got your what is included in this 400 megawatts. And maybe someone else could.
Yeah,
basically
come
engineering. So this is a scientific gain factor. There is a corresponding engineering gain, and there is approximately a factor of 4 in between. So this is a scientific goal. ITER is not going to put any electricity on the grid, but this is still much higher than what it was before.
So Q equal 10 is not where we're going to operate a reactor. So it's
not a reactor.
No, and when we go to a reactor, we have to have a higher gain factor. We call Q here, but that doesn't. But Q equal 10 is a milestone that has been set up for ITER, and that's what we're aiming for. It is proving that we can produce power. Then there's a question of how we set up the systems to optimize the energy consumptions in the systems around, especially in, for example, heating and current drive systems, which are very energy consuming, and which then consume more than the 10 megawatts that they're actually putting into the system. And I think that's at least part of the additional power that you were referring to.
Okay, thank you. You can come both here, because there's more questions. There's another question from the gentleman here.
Let me just extend it what Thomas said. The issue in all fusion devices is physics. Because the main problem is to have good confinement. And this is a truth which we discovered during a very long time. This is one of the reasons why fusion research takes so long time, to have a good confinement. So when we have this high Q ITER, we will address the regime when the main heating of plasma will be done by plasma itself.
Okay, maybe put a microphone a little bit closer.
None of you has mentioned alpha particles, which are also generated in this fusion reaction.
It was a lack of time, but you are absolutely right. The physics changes. The physics changes when you get Q above 1, and this is what we want to explore in ITER. This is something which we have not done in the past, and that's why. And it might be actually easier to get up to then Q equals 50 if you understand that physics. Depends on if nature wants us to get
Okay, excellent discussion. I don't know if there's any questions from the online audience. Were there any questions from the online audience? Oh no, one more question here. Go ahead.
Good evening. I am Marek Rubel from the Royal Institute of Technology.
You have to put the microphone close. Yeah.
Question to our colleagues from General Fusion.
Yeah.
To Michel, especially. What about the erosion or corrosion of materials by lithium? under such conditions? Is it really known? The second, I do not see in your concept the tritium plant, because you will produce tritium from lithium, but then you have to do something with it, and this is a huge installation.
Okay, I hope you heard the question, Michel.
Yeah, I did.
Okay, good.
The corrosion of lead lithium is quite bad. There's some material that are more resistive than other to lead lithium. Corrosion increased badly with temperature. So we analyzed that, and we cannot run much higher than 550 C on the hot side of the cycle, otherwise it'll corrode the pipe too fast. But at 550 C, with pipe of correct thickness, there's a corrosion rate depending on the flow rate and everything, and that have been measured because people want to use lead lithium for ITER, for example. So people have been doing quite a bit of work on corrosion. So it's a pain in the butt, but it can work. Like you can make pipe out of special stainless steel that can resist 550 with a flow in it, with a corrosion rate of, I can't remember the number, like 20 micron per year. Or, anyway, if you make your pipe thick enough, it won't burn. Then a tritium plant. Tritium need to be extracted as the lead lithium in the loop. You want to yank the tritium out of there and put it back in the fuel. It's a process extracting tritium out of lead lithium. We have not worked on that very much. Actually, ITER will have some lead lithium blanket, and they've been working on the process to extract the tritium out of this. We don't want to spend any effort and money on that thing. We hope that somebody will crack this nut for us. But you're right, it's a pretty big deal. Anything that has to do with tritium is a big deal because it's radioactive, it has to be safe and everything. So it's a fairly complicated thing, but other people are working on it, and they hopefully will generate something that we can use when we need it. If not, then we might have to work on it ourselves. But I would prefer not that. I prefer other people spend the money than us.
Okay, that was a good question. Are there any questions from the online audience? Not yet. So I had a question for maybe all of you, because we saw this like almost, I don't know what the scale was, but almost exponential growth in investments and startup companies in it. And I think you were in it in your presentations already, but maybe you can elaborate a little bit on what has made this possible, because I mean, you know, fusion technology, we have been talking about this for ages, but now we suddenly see a rapid technology development, which is of course very interesting, because we really need this, we need really an alternative to wind power and solar power. So maybe one of you can, maybe all of you can say something what you believe made this possible.
So I can start
maybe.
maybe.
Start?
Okay, yeah, ladies first.
Sorry.
Yeah,
so I just want to say that there are a number of things. One of them is, of course, the climate change and the awareness of that we really need fossil-free electricity. And like you said, factor 4. So it's really a pull. Which then there are also the technological differences, which we have seen: the computing power, material science, and then the private investments, actually. So there has been money coming in from the private sector, which has not been, we haven't seen that for a long time. So these are three main reasons, I think, which I think I'll stop there, maybe.
Yeah,
and also I just want to add that we are actually very close now.
Okay.
So we are actually going to see self-sustained fusion, hopefully.
Okay, let Michel answer. Now the debate really starts, and I know you have, and then there is a question from the audience.
Well, my point was the same as what you just said, but the big thing is that we're close. If you look at this graph with the Moore law, all those dots, they just below the line where you need some to make it, and people are recognizing that it's close. So now they start to invest money to try to finish it, because they can smell that if somebody succeeds on this thing, they're gonna make it big. Yeah? Like those investors, they don't do it for climate change or good art. They want to make a buck. So they can see that this is getting close, and they can see this is going to be big. So now they're starting to bet on it, and they've bet on 23 companies. Some of those companies will go bust. Maybe, hopefully, a few will succeed, and they'll make a huge amount of money on that thing. So I think that the big growth right now is because people feel that the goal is within reach now, due to those 40 years of research. And the other point are valid too, about global warming and all that.
Okay, Thomas, you had also, and there was another question.
Well, I can just agree with the previous speakers. I think
they have explained it very well.
Okay, there was a question from this gentleman here. You have to speak close to the microphone, yeah.
I'm Michael Tendler. I'm a member of EVA. So I worked for ITER International Organization.
Ah, okay.
And part of my job was to watch out for fusion spin-offs. Tunde has mentioned, you know, the superconducting technology.
Yeah.
So one of the very important spin-off which I identified is high temperature superconducting cables.
Yeah.
Which is basically the means of storage the energy, which is the nemesis of renewables. So because of these spin-offs, of course, ITER costs a lot of money, it's a huge device, but these spin-offs can, you know, very well make this effort valuable if there is, we all know that, for example, World Wide Web came as a spin-off of LHC project.
Yeah, what would we do without it, right? Yes.
Came from Apollo project.
Yeah.
So very often when you make a huge international project, you get spin-offs which covers all the enormous costs which it makes itself.
Okay, thank you. I have another burning question because I'm originally from the transmission industry. So as we said, we see the production needs to quadruple, so we need to go to a factor 4 increase, and we have now this combination with non-regulatable sources like solar and wind. So the burning question for me was that I had is this regulated? Is this regulatable or regular? So can we use it to balance supply and demand, right? That would be fantastic.
So this is in my view, at least the magnetized fusion is not very well suited for regulating the power. It's a base power source. It will produce a continuous source of energy uninterrupted at fairly large power. However, the fusion power is obtained at a bit of a not a sweet spot, but at you want to push your fusion power up to an optimal point where you're working, and if you want to reduce your power output from this optimal point, you then start getting into competition with for example, the other system, that what we talked about, the Q factor, that you have other system that consumes heat as consume power, and the economics of your power plant is going down if you want to now produce, if you want to regulate the power.
It's easy to regulate.
It's easy to regulate. That's fantastic news.
It's economical to regulate fusion power.
Yeah.
You have to boil water and this system which you have to heat up.
Oh, we have to give you the microphone because now it gets interesting. So.
No, I don't believe it's easy to regulate. Of course, you have a short pulse for a very short time, but the system, you are boiling water and producing electricity in this way. You cannot. It takes time to heat it up and cool down. As an ordinary nuclear power station, you can. That is what takes you cannot regulate that.
No. Well, that's a pity because that we need. But for this enormous and extra generation that we need, this would be a fantastic solution. Are there any more questions? Or I forgot to print out what my questions were, so I have to improvise a little bit here. But I found this very interesting. And if you look at the North Sea, where we actually have planned then 400 gigawatts wind production to place, and you look what it was the sizes between 200 and 400 megawatt, we need 1,000 of these plants somewhere in Europe, and you talk about 1 kilometer by 1 kilometer or 2 kilometers by 2 kilometers. That is of course much less land space that we need for this than we need for an appropriate amount of wind power, so that's actually quite good news for the biodiversity. But what would be a good location for if we manage, you said also, Michelle, we're quite close. What would be a typical location for these kind of power plants? Because this is a bit bigger than the power plants we have now. So what would be a good place? Would it be fantastic to put very close to a data center, which is at 300 megawatt? So if we have a data center and we build a fusion plant beside, and we don't have the transmission in between. So what would be a good place to place these kind of fusion power plants?
You want to take it? So there is no real restrictions, of course. The main thing is that it doesn't require a huge land use. And sometimes, I mean, there are very many advantages with fusion, as he mentioned, safety, and also the fuel is widely abundant, but also this not too much land use. Even if we have certain parts of the world where are possibilities, but for example in India, when the population density is very high, you can't really put so much. So depending on where you are, so there is no real restriction. But your idea of putting it close to the data center sounds to me like a perfect way. But
yeah. Okay, I see Robert has their hand raised. Maybe he wants to add something.
Yes, certainly. Yeah, so this is actually one of the things that we're trying to work through right now together with our potential first mover customers. So is the best use of this for a data center, or is it for a city, or is it for to replace a large 1,000 megawatt power plant, or is it best to use this kind of up in the north for hydrogen generation, for fossil steel, etc. That's a thing that I think that we will be working through in the next few years to have an understanding of how does this technology play into the mix with hydropower, wind, solar, and also existing nuclear generation. But that's a question that we will have to work through together with the big power producing companies and those that are in great need of clean energy.
Okay, I think you wanted to add something, Thomas, or?
Yeah, I think Robert is also. I think what Tunde was saying is quite important. There are not that many restrictions. With fission, we used to have power plant next to Copenhagen, which wasn't very popular. And I think if you put a fission plant next to Copenhagen, they would not mind at all.
Okay, well that's very good news. I mean, and then. One of the things that you said triggered another question because I mean it's the levelized cost of energy. It's going rapidly down. You know, the cost of solar panels is going down. The cost of offshore wind is going down. Where do you think, or where might we end up with fusion power? Will it be, let's say, competitive price-wise? At the end, or we don't know yet, or
maybe I can start. So of course it's very hard to speculate. Nobody knows what the oil will cost in 50 years from now.
No.
So it's hard.
Let's
to
hope that it costs a lot.
Competitive. Yeah, probably it will be unreachable cost. But still, I mean, the experimental devices that we build, they are costly. Nobody knows how to actually build these. But for these lower, smaller, which I mentioned, Spark, and the capital cost is the main thing, and the magnets. And this is why they try to reduce the size of the magnets.
Okay.
And so if you can reduce the size, then you gain a lot. And of course also the availability, how to. Because sometimes you need to maybe, if something breaks, then take it out, and then you have to shut down, and all these issues come in, which we are not used to. We are working with plasma physics. But every estimate seems to come to the conclusion that it will be comparable to contemporary fission power plants, because the capital cost is very high. It's not so, there is not much for the fuel, but there is a capital cost which is comparable.
Yeah, and I think that would be interesting discussion as well, because I mean now with the enormous amount of wind power to be built, we need to invest an enormous, a vast amount of money actually in transmission line, and if we could put this type of new power plants actually where we see the increased need for supply, so close to data centers or close actually to large industry which is going to decarbonize, then that could be a fantastic idea also to reduce the infrastructure that is needed to be built, which is also a challenge. We have another question, another comment.
Let me just add up with all these renewables.
Maybe you
put intermittent, yeah?
Yeah. Yeah.
So intermittence introduce enormous problems, as we can see now. So it depends on the weather. It depends on many. Look at Germany, German example. They have built enormous amount of renewable energy, and still they have problems. They have to burn some coal. So
exactly.
Intermittency poses a very difficult problem.
Yes, it does.
Here, of course, fusion energy will be very expensive, to be honest, from the start. But when nobody knows what will be the alternative, and on top of it, it provides the basic energy.
Yeah, and exactly. I think if we're going to go for this type of technology, we have to look at the cost for the society as a whole, and then of course building wind power might have one price, but we need to build a transmission line. But if we could put these very close where the high consumption is, then we skip the cost for transmission lines, and that could be of benefit of the society as a whole. So. Yeah, Robert.
Yeah, I just wanted to touch on the subject as well. Yes, with plannable energy production, one can certainly demand a premium on the price for that electricity generation compared to intermittent generation like wind and solar. But I think the answer here is also that we absolutely have to target to be competitive with coal. And it's not just for European conditions. We need to be competitive with coal for the entire world. So that's where we're shooting for being with this technology. It's not about just creating an energy system that works in Europe or in North America. We need to be competitive in the world with coal.
Yeah, I don't know if there's any other questions. Yeah, okay, there one.
Yes, hello, the Birgitta Resvik. I'm also a member of this division. I'm just interested to hear about this really increase about the private companies starting to invest. And as you say, there's a lot of thinking that we are very close to it. Could you say anything about who is the investors?
That's maybe a question for Michelle. Yeah. I also started to be curious.
Our investor, there's a Canadian fund, like some bank and stuff like that. Okay. We have some big. Kazana is a fund from Singapore. We have money from Jeff Bezos, a billionaire, who wants to go to space with fusion. Doesn't really want to make electricity, but he gave us some money anyway. And so there's a variable thing. But now that you get into a big money, when the machine get bigger, you need big funds. It's not going to be small fund anymore. So those national funds, like from big country like the Saudi or stuff like that, that's where the big money will come from for more, in my opinion.
So I can send you this report with which I took a couple of, and then these investors are listed there. And as he mentioned, for like 10 years ago, it was mostly philanthropists like Jeff Bezos, Bill Gates, and people who wanted it. But now it's actually energy-producing companies like oil, and they are getting into this, interestingly. And they are getting into like approaches which have high triple product and going for the not cold fusion or any of these weird things. Which so I can send you if you give me your, because that report includes all that information.
But that's actually very interesting to hear, because that means, as you mentioned, that it's I mean, if the banks start to invest, and you see a change in the investor landscape, then people start to believe that, you know, we're getting closer at least. And that would be, I think we're about in time to close the seminar if there are not any burning questions. I think that's a very positive way to end this seminar. So I would like to thank all of you for your excellent presentations, and I think we can go to dinner or to bed or to lunch with the knowledge that fusion power might actually be a solution for a carbon-free energy system, and I think that would be a good message to give to the young people out there. Okay, thank you very much.
Thank you.